So the other part of today is to do the lab. So I posted the material on Moodle at, yeah, so it's still in Gibbs sampler and MCMC. So it's lab 3, Gibbs sampler for beta binomial. Yeah, so this again, so we're still like in the paper, we're still talking about how we can replicate the results. So I will ask you to do this. So if you open it, you see that I'm trying to ask you to replicate example 1, and in particular figure 1. So figure 1, if you remember, is talking about a bivariate distribution, and they jointly follows a PDF showing in equation 1. So this is just some summary from, oh, I should say, to share this. Okay, so the instruction here is I gave an overview, which is summarizing from the paper, that if you have a joint distribution of x and y, PDF in this way, then you are able to actually derive the full conditional distribution for each of the 2 parameters. One is a binomial, the other one is a beta. And you can see that they're intertwined, right? Say like for equation 2, the full conditional distribution for x is a binomial conditioning on y, depending on y, right? And then once you move to the full conditional distribution for y, it's a beta that is conditioning on x. Okay? And then, of course, the particular setup that they have is, if you look at the marginal distribution of x, it's a known distribution. It's called beta binomial. Okay? And then it has this slightly complicated PDF that you are able to do. So this gives us, I think, the chance to check and then to sample. One way is from the beta binomial distribution directly for the x. The other one is to simulate from a Gibbs sampler. Okay, and then we can verify. So the paper, I think, the figure 1, if you remember, they did talk about how they match or not match well enough. So this is a lab I hope that you will find interesting and useful. And in particular, I gave you in section 2 like a particular package called VGAM. If you install it and load it, you're able to generate random draw of beta binomial distribution. Okay, so you're able to generate the marginal of x. So that's what section 2 is about. Section 3 is just a quick summary that you should do this Gibbs sampler iteratively. You draw x given y, and then y given x, and then you save your draws in the end to do the summarization. And then section 4 is like listed out like different questions. You do this one by one, and in the end, I gave you some hint as how you can plot them in those side-by-side histogram that they have in the paper. Yeah, so that's one thing to keep in mind. And question 3 here is it's just an in-between question, intermediate question there. I asked you to think about, oh sorry, question 2 here. I'm asking you to think about how many Gibbs samplers or MCMC chains that you need to run in order to replicate what they mean. Okay, so you just need to write it down a number and then go from there. And towards the end, hopefully, I don't know if we have time, but I will walk around to answer questions. But I sort of figured out how you can do parallel computing on your own computer. So I will try to give some demo. But before we get there, I still want you to first have a general like structure of how your code is going to be in order to replicate the results. Because once you have the main part, we are able to move to think about in what way we can trick this into parallel computing. Okay, so all right, so let's just have the lab time, and I will walk around to answer questions. Yeah. I think one thing worth mentioning is, so question 1 is you're just going to draw from this marginal distribution, so it's a multi-column draw, that's okay. And then when you try to do the Gibbs sampler, some of you are referring to the lecture slides that we have, which is a good place to go, of course. And remember, we did the demo of doing something we called, I think here, yeah, so it's the lecture, like this lecture, and then on page 14. So this is a demo that we did in class, and then also we did an exercise on. That is writing a function called Gibbs underscore normal, and then you run a super long chain of the Gibbs. Okay, so that's a place to start, but I want to give a heads up because the paper is not running a super long chain. The particular example that they did is not running a long chain, but it's running many short chains. Okay, so that's the part that you should start thinking about how I can. So most likely you're going to use a loop, right? Most likely you're going to use a loop, and then how can I run multiple chains using a loop, and then keep in mind that you're saving only the last row. So play with this, and I mean, yeah, if you have questions, I will and I try to answer them. But this is a place to start. But again, it's different from what we have been doing. Okay, so that's the new stuff. Yeah.
Does it matter which parameter we initialize, or does it?
I don't think it matters. Yeah. Well, you can try and then justify it, but for now, just start whichever you prefer. So I think many of you are all like moving to the Gibbs sampler part. So maybe let me just ask really quick for question 3. According to the Gibbs sampler implementation that they described in the paper, how many Gibbs samplers or MCMC chains do you need to run? 500? 500, right? Yeah. So it's very important to read it carefully. So what they say in figure 1 is they display, I mean, 2 samples of size m equals to 500. And then they have specification, right? So the n is 16, alpha is 2, and then beta is 4. So you have to use all of them, follow what they use. I mean, that's what we mean by replicating the results. And also good to keep in mind that some of you were asking, well, since I'm running like short chain and then I'm running many chains now, do I need to do the burn-in? Do I need to do the thinning? The paper didn't say. It sounds like they only just saved the last straw. So no worries about the burning and the thinning for each of the chains that you run. But keep in mind that you are running 500 chains. So think about how to incorporate that into the loop. So you're probably going to have some kind of nested loop, right? Out there, you have to loop the whole thing for 500 times. Okay? And within that loop, you have another loop, which is doing the actual Gibbs sampler. Okay? So that's my hint. So let me just quickly talk about, like a possible approach that you can do. Because many of you, I think, are referring to the script that we did for the normal case, which is good. Over there, as you notice, we only run the chain once, right? And then the 2 full conditional distributions are much more complicated than what we have right now. So I would suggest you to build up the Gibbs sampler first, which is only having 2 lines essentially, right? How to draw X and how to draw Y. And if you look at what we have in the document, draw X, you go from equation 2, right? And draw Y, you go from equation 3. So these are the 2 full conditionals. So essentially, I get X from R by norm, and then relying on N and Y, right? And then for drawing Y, I do R beta, which depends on the X, the alpha, the N, and beta. Okay, so you build up those 2 lines first as your key component of the Gibbs, then you're able to do the rest. So I have, which this stuff I will upload later as well. So this is what I came up, and say you set the seed. I know how many iterations I'm gonna run. This is the iteration for the Gibbs, okay? We have 2 loops here, nested. One is, because we're gonna run M, which is 500 number of chains, right? So that's the bigger loop, that's the outer loop, yeah. And then within it, we do a short loop, because that loop, the inner loop, is doing the Gibbs sampler, okay? So the highlighted part is the one that I'm suggesting that if you don't know how to start, build the smallest part first. Okay? And the first part we know is to run 1 Gibbs sampler. Okay? So the way to run 1 Gibbs sampler is through a loop, right? I have X from its binomial distribution. I have Y from its beta distribution. I fit in whatever that is, like all of the values of N and Y, X, A, and B. So this part, the highlight part, those 4 lines here, is 1 Gibbs sample. And then of course, so this is just personal choice. I decided to initialize the chain with y, and I fix what y is. So I just, every time I start with y equals to 1. This might not be a good thing. So maybe I should do, so y is the beta. So let me just do a random draw of beta. What can we do? Beta 1, 1 is uniform, right? So let's just do that. So we can actually have different initial values every time. Okay, so this might be, I think this is a better practice than what I did earlier. So this few lines all together is doing one Gibbs sampler. Okay? And this is, as you can see, much simpler than what we did in class. I mean, for the normal case, again, normal, both of the full conditionals are pretty complicated with the parameters, whereas here, the beta binomial is much simpler. So you see that I'm not saving like y's. You can save y's, but per question, we actually only need to save the last raw of x. So you see that I'm not even tracking the chain. I know that once I'm done with this loop, my last x is going to be the x that I left with from this loop. It's going to be the last x that I need to save. So that's why I just add one more line here, which is a vector that I initialized earlier with length 500. And then I'm saving for this particular Gibbs sampler, I'm saving the last x. So it's a nested loop. Outside of it is because we are running m different chains. Okay? And then inside the inner loop is doing the actual Gibbs sampler. Okay, so what we did in class is only the inner loop, but it's a much more complicated inner loop because we have more complicated full conditional distributions. Here is simpler. So if you do this, and of course, if you have your other, like the from the R beta binorm AB, that function out, then you should be able to plot them together. And I introduced in the write-up that you can install this Plotrix package loaded, and then you're able to do this side-by-side histogram like what they had in the paper. So notice that I'm setting the breaks in this particular way. Just want to make sure that it's those integers that is showing up on the x-axis. Okay, you can play with that. That's some extra function that you can do. Okay. Does that make sense? That we're running it for 500 times, and then within each of this, we're doing a Gibbs sampler. Okay. So in class, we only do one loop because we are running one chain. Okay. Right now, we're running 500 different chains, so we're doing a like a loop over 500 times. Okay. And another difference I would say is back then we're saving every iteration of the two parameters. Here we're not. You're welcome to do it. It's not required because for this question that we're trying to replicate the results, they only save the last raw of x from each chain. So that's why I'm only saving the last one. Okay. All right, so that's so much. I mean, I'll upload this for you to check. And for the last 4 minutes, let me just quickly talk about my basic understanding now of how you can use R and RStudio on your own laptop to do the parallel computing. So one thing you should first do is to check how many cores you have on your computer. So I'm sure you have other ways to do it. The only way that I know is this package. You download the Snow package, load it, and then you run this one. Parallel, and then detect cores. You will know how many cores you have on your computer. Okay? So remember last time when we had the discussion, Ross told us that if you are running m different chains, if you have 4 cores, then you can set m over 4 number of runs for a particular core, right? So for us, we need to find out how many cores we have. So because I'm using, let's see if I can use it actually, because I'm using the RStudio server. Let's see if you can access that. But if you download and okay, so this computer has 8 cores. Yep. And so that means you can set like 8 different parallel computing like skills to do this. So what you can do is, so I was wondering how you can do this. Maybe not like the smartest way, but you can do it. So what I was told, so I consulted a colleague in neuroscience, and what he told me is in R, what you do is, so here we have 8 cores in this computer, right? And how many iterations we're doing? 500, right? So if we divide it by 8, well, it's not a, yeah, roughly. Let me just suppose we have 4, so that's easier. Suppose we have 4 cores, and then so that means on each computer, no, sorry, on each core we should try to run 125 not chains, chains, 125 chains, right? So what you can do is you just open 4 different RStudio, and then, no, that's how it works. And what you do is change, no, don't laugh. So start a new, let me do that for you real quick. So, yeah, start a new one. And so now instead of, so let's do like M now becomes 500 divided by 4. Okay, divided by the number of cores that you have. So now so that's why a good practice to define those outside so you don't have to change all of those numbers later. And then you open 4 different RStudios, run the same code. And then you're gonna come back with, I think, 4 different, obviously, 4 different beta binom draws Gibbs based on the way that I define it. Each of them gonna have length of 125 instead of 500. And then in the end, you just put them together for your analysis. So that will be a quick way in order to do parallel computing on your own computer. Okay. Yeah. So first of all, we find out how many cores you have on your laptop. In this computer, there are 8. My own laptop only has 4. So, and then plus we're doing 500. So just to make it easier as an integer number, I'm assuming we're going to use 4 cores. So what you do is you define your M, the new M, to be the number of chains that you're going to run divided by the number of cores. And then since suppose we have 4 cores, you're just going to open 4 RStudio, and then you run them like one by one, and then you're going to get what you have in the end. Okay. So the outcome will be 4 different vectors, okay? And each vector is length of 125. So when you run 4 of them, you're going to get 500 draws in the end, right? And then you combine them to do the final analysis. Yeah. So of course, yeah, it's a little bit tricky because then you have to save all of the draws and then like combine them in the end and load them. So it might be more tedious than what you do, because if you run what you try, like say when I run this, it was super fast. Yeah, I don't even need parallel computing for that. So not the greatest example to demonstrate, but if you want to try doing it, find out how many cores you have and then change what you want to do in terms of the number of chains for each of the programs. Okay. And I noticed that I think because this paper is pretty much the only time that we're trying to say that we're gonna run multiple chains, right? And then like multiple short chains that only save the last draw. So this might be the best time for us to talk about what if you want to do parallel computing. Because later on in the semester, we're typically gonna run one more chain, okay? And then do the burn-in and the thinning to make sure that we have independent draws from the posterior. Okay. All right, so so we're gonna end here, and for this lab, it's due that Thursday after we come back from break. But I think most of the material is there. I will upload the sample script that I have on Moodle for your reference, and you don't need to do the parallel computing part for that.